So when we think about our substitution reactions, pretty much the whole of chapter 8 and 9 that's in reference to substitution all comes back to this one slide. Okay? So when we go through and think about them, what we're thinking about is, well, how could they possibly happen? This is why we have SN1 and SN2, because there are two ways that you could go through and either make and break these bonds, or then make these bonds. Okay? So when we ended, I said one of these was invalid. Okay? Make, then break. Okay, so if we make the bond first, what are we saying happens? The octet is the conclusion. What I'm asking is, what are we saying happens? Too many electrons is again the conclusion. I don't want the conclusion. What I want to do is go back up to my drawing up here and say, what does it mean to make the bond first? The chlorine will take its lone pair of electrons and it will attach or attack the carbon. Okay? I'm taking the negative charge of that chlorine and I'm pairing it with the what am I pairing it with?
The neutral carbon.
The neutral carbon. If I'm pairing it with a neutral carbon, couldn't I have just as easily done this? Or this? Or this? Right? Why are those wrong? No, what'd you say? That is an alkyl halide, but all of those carbons are part of an alkyl halide. Okay? We've got Lee pushing to an idea here. That position has a leaving group. As a leaving group, what does it do? It can withdraw electrons from the carbon. Why does it withdraw electrons from the carbon? Because it's more electronegative. So is that indeed a purely neutral carbon? No. It is partially positive. So why does that negative chlorine go to that partially positive carbon? Carbon. It's getting worse. Okay. The chloride is negative. I'm trying to stabilize it by pairing it up with a positive. That's what's happening. Okay? It is that charge balance that's what's occurring. Okay? So let's erase all of those horrible arrows because they're bothering me, even though I have excess through them. What would the result of that arrow be? Okay? Because if I make, then break, all I've done is made the bond. That's what that arrow means. I'm taking a pair of electrons on an atom and I'm sharing them with another atom. That is literally the making of a bond. What does the end result of that step look like?
A formally positive carbon, a formally negative carbon.
No. Okay, exceeding the octet is again the conclusion. I want to draw the structure first. Does the iodine break yet? No. If I draw on that arrow that the iodine is breaking off, I'm not making then breaking. I'd be making and breaking. I said making then break. I need to make the bond first. What is the result of making that bond look like? Okay, that's the first answer that's starting to get towards that. That's good. Okay, did I do anything to the carbon backbone?
No.
No, which means?
It looks the same, except it's not.
It looks the same. Did I do anything to the carbon-iodine bond? No, so it looks the same. Did I do anything between the chlorine and the carbon?
Yes.
Yes. I'm now showing a connection between them. There's that bond. Okay, and for the sake of color coding, we could do that. Yeah? And I heard a lot of you go through and say, well, we've exceeded the octet. Really? Yeah. Okay. A lot of people will goof on this because what do we forget about? The implied hydrogen. Have I shown anything happen to that hydrogen? No, which means it's still there. Okay? If I had the iodine leave, would I end with the result shown? Yes. Am I allowed to do that?
No.
Why not? This structure is invalid. I'm not allowed to draw it. I don't care what can happen afterwards. It's irrelevant. Okay? I'm not there. I can't do that. Okay? Make sense? So we're not allowed to do step 3 because when we draw, when we translate the English language using our curved arrow mechanism that we learned back in Unit 1 with resonance, we draw this result and we know that structure is invalid because in Unit 1 we learned that carbon can't exceed its octet. Okay? Which means that mechanistic process doesn't work. Okay? So there aren't 3 ways to do this, or 3 valid ways to do this. There's potentially only 2. Every mechanism we ever talk about, this is literally what's happening on the back end. Someone went through and said, well, what happened? I made a bond, I broke a bond. How could I possibly do that? Here's the ways it could possibly happen. If it happened that way, what would the result look like? What would my mechanism look like? Can I find experimental evidence to prove that that thing exists? Yes? Then that mechanism is valid. Do I find experimental evidence to prove that that thing does not exist? Then that mechanism is invalid. Right? So when we talk about mechanisms, they aren't these things that people just sat down and said, ta-da, it's going to do this. We look at the beginning and the end of a reaction and we say, okay, well, how could that happen? We come up with those lists of things. Okay? So we got 2 other options there. Do we want to take a look at those? Silence, that's always fun. Do you want to look at those other options? Okay, I got at least a head shake yes. Which one do you want to look at?
Break, then make.
Break, then make. Okay? I'm going to have to remember I got to use the silly eraser this time. So we go back up to this process. Might even be a good idea that we leave the hydrogen in there and we note that that carbon is partially positive because that helps to identify the chemistry so that if I was going to go through and try and solve this question, those things are now drawn in and I know that I have to keep them in mind. Why were they not immediately provided for you?
Because you're supposed to know.
You're supposed to know. Okay? That's why they're not given to you. If you advance further on, you're supposed to know these pieces. Okay? Is that a chiral atom?
Yes.
Yeah. Shouldn't I show wedges and dashes? Yeah. Shouldn't I show a wedged hydrogen and a dashed hydrogen at the next carbon? And at the next one? And at the next one? Why did we not do that? It's implied. Why did I imply it?
Okay.
Why am I implying all of this?
That's a lot to write.
That's all it is. There is so much information that I could theoretically cram into every single drawing. I don't do that. Okay? And I remove it down to a basic skeleton structure, and I have to remember to put that information in. That's why we talked about it in Unit 1, because you have to remember to put that information in. An advanced organic chemist doesn't need to show that hydrogen. Why? Because they know it's there. Okay? They don't need to show the partial positive charge because they know it's there. Okay? They've had that practice. You haven't had that practice yet, so you should probably show that. That will help to guide your work. If you don't show it, you don't have anything to guide your work. You're trying to be an advanced chemist. That's awesome. Kudos to you. Okay? There's a reason you're not an advanced chemist. One of those reasons, you're in this class. If you were an advanced chemist, you wouldn't be in this class. So don't treat yourself like a complete advanced chemist. Show all those intricate steps. Okay? So I heard a make then break. Okay? And I really don't want to deal with wedges and dashes right now. So we're not going to show that. So what does it mean to make? Or we said break then make. Okay? I heard someone say break then make. So what does it mean to break? I need to break a bond. Which bond do I break? Okay? Why would I break the carbon iodine and not the carbon hydrogen? Iodine is more electronegative than the carbon. That bond is more polar, more likely to already be in the process of breaking than the carbon hydrogen. Carbon hydrogen is so close in electronegativity that it's not in the process of breaking. Okay? So we can go through and we can show that. We can highlight the fact that that bond is breaking. How do I show that that bond is breaking? I'm going to show how the electrons are moving. Well, what are the electrons that I'm moving?
The two between iodine and carbon.
Okay? So an interesting reference, the two between iodine and carbon. That's awesome. I don't see two electrons. What do I see?
The line.
A line. What does the line represent? Two electrons. All of those pieces are things that you need to be cognizant of and representing through these actions. I start my arrow at the line because I'm breaking that bond. I'm showing where those electrons are going. They're going towards the iodine. Why to the iodine? It's more electronegative. Okay? That single arrow, I can now show a result. Because this says break, then make, I can't show anything happening with the make until I've shown the break. I've provided the instructions, but I haven't shown the result. Okay? Before you start busting out an eraser, I'm going like, well, I'm just going to erase that. What was your arrow doing?
Evaporating.
Okay? When we show instructions, if I ask you to draw a star, is that good instructions? Draw a star. No. How would you draw a star? Step 1. Step 2, show a second line. Step 3, show a third line. Step 4, we show another line. You slowly build on it. Okay? We have to show each of those intricate steps. The same thing is happening in OChem. Okay? For better or worse, you may not like it, that's the way we do it. Okay? So let me fix that thing. Let's get that back. What's our result? Okay, I'll accept that. We get an iodide ion chilling on its own. I'll even go through and show that red dot, or the red lone pair. What else? I don't accept a carbocation. I don't accept the negative charge yet. I'm not saying those answers are wrong. Okay? But I want you to get focused on the process behind this first. The process we're mirroring is exactly what we did in Unit 1. Why would you draw a positive charge?
Because you have to keep the balance of charges. If you create a negative charge.
Okay, so I draw a positive charge and a negative charge. So there's my answer.
No. It has to be on a specific atom.
Okay? The drawing of a charge needs to be associated with a Lewis structure. If you don't have a Lewis structure, don't draw a charge. Okay? Whoa. Go away, letters. Okay, so now let's draw out all of those carbons. Okay? Now I can evaluate my charges. The iodine started neutral. It now has an extra pair of electrons. Most people jump all over that one, and they call that one negative, and that's fantastic. I really like that. Okay? I would argue that we've already made a mistake. And by we, I, because I was the one that drew it. So I take full responsibility. What did I make a mistake in doing?
You didn't.
I drew a hydrogen for a reason. I just deleted it. Okay, why did I delete it? I'm falling back in my old habits of, I just know there's one there. Okay, you aren't there yet, so let's make sure that we don't just delete it. So I could show it like that. Okay, roughly mimicking, stupid letters. Roughly mimicking the way we had it drawn originally. Okay, would that be a correct Lewis structure?
No,
Why not?
because you haven't done formal charge.
I need to address that formal charge. That carbon is positively charged. We talked about multiple ways to determine that charge. Okay, you need to rely on one of those. Okay, I don't want to discuss it again. The next thing I do want to discuss here, is that a good drawing?
No,
No, why not?
because you still have CL present and you haven't shown that.
The CL has nothing to do with that drawing.
Hydrogen wouldn't be in that position straight up.
Did I accurately represent the three-dimensional structure?
No.
No. Okay, I'm showing roughly a 180-degree bond angle and then maybe a 60 and 120. That's a crap drawing. Okay? I should do the best I possibly can to mimic the actual three-dimensional structure. Unit 1. Okay? Why? That can help me get a better understanding of where those atoms end up with respect to each other in the end result. Okay? Now is my drawing better? Yes. Okay? Did I break a bond? Yes. So now that I've broken a bond, then I can make one. Okay? How do I make one?
Find something that has electrons to share.
Okay? I just drew a result that had a positive charge. That positive charge is unstable. What does it need? Electrons. Where can I get electrons from? Could get them from the chlorine. I could also get them from the iodine. Why am I deciding to take them from the chlorine?
Because if you did the iodine,
Because I just broke the iodine off. Fair enough. What else?
we know that we're going to end up with chlorine iodine.
Look at the answer. Okay? The answer is given to us in this case. Let's use that to our advantage. The answer says the chlorine needs to attach. So there's my arrow. I'm taking the electrons from the chloride and I am sharing them with that positive charge. What would the result be? It would be that structure there. Okay? We didn't even show that hydrogen in there now. Okay? If we break this all down, we've got three arrows. Arrow 1, and I'm going to call it arrow A and arrow B. These are our reaction arrows. Or sorry, not our reaction arrows. Yeah, we'll call them our reaction arrows. What does arrow 1 represent? What kind of reaction? Okay. Heterolysis is a suggestion. Remember, I went through and carefully labeled these. Arrow 1 is that purple one right up at the top. Is the only thing I did breaking a bond?
No.
No. So I don't accept heterolysis. What did I do?
You remove and make.
Okay. There was an iodine there. The iodine is gone. Now there's a chlorine there. For arrow number 1, what did I do? A substitution. Beginning to end. This would be a substitution reaction. Okay. For arrow A, what did I do?
Heterolysis.
This is now the heterolysis. Hot sauce. Ouch. Heterolysis. What did I do for arrow B? Coordination. Is this a heterolysis reaction?
No.
No, that is a heterolysis mechanism. That's not a coordination reaction, that's a coordination mechanism. If I take a heterolysis mechanism, follow it with a coordination mechanism, I get a substitution reaction. Okay? Are there other ways to get a substitution reaction?
Yes.
Yes. Okay? In fact, we've listed 2 ways down below. We just identified one of them. Okay? So what we might want to do is differentiate this substitution reaction mechanism from the other one. So I will go through and call it a substitution because that is what it is. It is a substitution reaction. But that reaction goes through 2 mechanistic steps. Those 2 mechanistic steps set it apart from the other one. Okay? So I'm going to call it a substitution type 1. Why type 1? I'll accept that because there's a type 2. Okay? What did I do? Break, then make. What was it named? 1. That's why I'm calling it type 1. Okay? In this substitution reaction, I now want to evaluate the pieces that were involved in it. Okay? The heterolysis split the bond, and then I had something attack that structure. What was the name of that something attacking? Chloride. Phenomenal answer, not the one I want. It was a nucleophile. So while this is a substitution, it is a particular type of substitution. Okay? This substitution involves a nucleophile attacking the structure. So I will call this a substitution nucleophilic. When I put that all together, I get SN1. Why did we use the 1 again? Why did we call it 1? Because it was type 1. Why was it type 1? Because I wrote the 1 next to it. That's a pretty horrible reason to call it type 1, because couldn't I have just swapped it around? Yeah. So that would really suck for you as students to memorize that SN1 is this because someone arbitrarily started with it. Okay? When you learn biochemistry nomenclature, you'll hear reference to an alpha and a beta type of sugar. Guess what alpha meant? It was the first one discovered. They're literally calling them type 1 and type 2, but in Greek, because they found them in that sequence. Okay? We actually have a legitimate reason behind calling it type 1. Okay? That legitimate reason has to do with how this reaction proceeds. So it has to do with the mechanism. So what I'm going to do is erase out that reaction. We're going through step A, step B. How many steps is that? 2. So that is equal to... No, that wasn't 1. Okay, this was something else has got to be here. Okay? When I run a reaction that has multiple steps behind it, which of those steps is the most important? The slowest step. The slowest step, and it's so important that we don't just reference it as the slowest step, we call it the rate determining or the rate limiting step. Those are familiar words. Those should be words that you learned in Gen Chem 152. Guess what you get to do? Which of those steps is the rate determining step?
Step 1.
Okay? We're calling them A and B in this case, so I'm going to assume you meant A.
Yes.
Okay? Why would step A be the rate determining step?
It's the most difficult to go through.
Why is that first step going to be the most difficult one to go through? Okay, we could use the breaking a bond. That's not a bad idea. It requires more energy. Why would it require more energy? And it's an interesting reference of words because that would assume that we were looking at energies. Does anybody see any energies up there? No, maybe what we should be looking at would be an energy diagram, where we're starting with our reactants. those reactants go to make, do they go to make a product? That very first step, is that the product? No, what is that? That's an intermediate. Is that intermediate higher or lower in energy than our reactant? Higher. Why? It's charged. Hell yeah, there we go. There it is. Boom. Now in that second step, going from the intermediate to the product, where should I place the product energy? Lower than the intermediate? Why? Why is it now stable? No charge. Okay? If this reaction was a successful reaction, we might draw that below the reactant. Let's not stress necessarily about that yet. So we would draw something like this. So when we're asking about the rate determining step, we're asking about the activation area to go from reactant to product and what's the other activation barrier? Intermediate to product. Which of those is going to be the slower step? The larger arrow. It has a larger activation barrier, which happened to correspond to our rate determining step, which would be step 1. So it's 1 because it's the step 1. Okay? No. Sorry. Another random correlation that just happened to fall out of nowhere. Okay? What I'm going to expect you guys to go through and do is this exact same analysis with the break and make. In the break and make, we'll call it SN2. How many steps are in the SN2? 1 step. Which will be the rate determining step in that 1-step reaction? The first step. The number 1 has nothing to do with the steps, okay, per se. Okay? Because you guys were so awesome in 152 and you nailed that first step was the rate determining step, you can now tell me the next thing. What is the rate law for that first step? That would be rate equals, and in fact this will be rate of A, step A, equals K, which would be the what constant? The rate constant, which would be a lowercase k, which I'm horrible at drawing. Okay, not an equilibrium k, so lowercase k, times what? Concentration of the product over the reactants, and thank you for saying that. Unfortunately, you are wrong, but we needed that. Products over reactants is K. For what? The equilibrium constant. This is why people hate 152. You have 2 Ks that you have to work with. One's lowercase, one's capital. They mean entirely different things. Capital K is the equilibrium constant, products over reactants, not rate law. So rate A times K, the rate constant for that step. So the rate is constant? No. What would be the rate for you finding a partner? Trying to not, like a significant other. There we go. What's the rate for you finding a significant other if you're the last person on the planet? 0. Okay? If that's my rate expression, rate equals the rate constant. Well, constant's a constant. Okay? What would your rate be? You just said it was 0. Is your rate 0? No. Maybe we're missing something. If we added another person, does the rate go up for you finding a partner? Yeah, what if we add 50 billion people? Oh, the rate goes up a lot. What did we just change? The concentration. And in particular, the concentration of reactants. Okay? So what you learned in 152 were all of those things that affect the rate for a reaction. Okay? One of those things is concentration, and in particular, the concentration of reactants. So let's take a look at step A. What are our reactants? Okay, I heard reference to a nucleophile. What was our nucleophile? Specifically, the chloride. There's our nucleophile. So yes, this is kind of confusing because we got pieces everywhere, but this is part of it. I want you to see those pieces and start to tie them to their correct locations. Is that nucleophile involved in the first step? Our first step is heterolysis. Where does the nucleophile come in? In the second step. So the nucleophile is not present in the first step. What is present in the first step? Okay, sort of the leaving group. It's not the leaving group officially because it's still attached to the structure. So we would reference that as the substrate. Okay, in this case, we could go through if we wanted to be really less specific about it. It's this guy. Or girl, depending on how you want to personify your chemicals. Okay? It's that species. Is there any other reactant?
No.
No, that's it. What is the order of this reaction? Stop talking about 152. Sorry. It is first order because there is only one concentration in my rate law. First order, also known as unimolecular. When we reference the substitution nucleophile, it says type 1. First one. Yes, that is exactly why it's type 1, is because when we look at the rate determining step for this reaction, there is only one species in the rate law. That is why it's an SN1. This is why sometimes you will see it not written as type 1, because that was a bit weird. I'm going to be honest about it. It'll get written as substitution nucleophilic unimolecular. What is it referencing? The rate law. Okay? We literally just did like all of SN1 right now. Okay? That's pretty insane. Okay? So some of the stuff that we introduce with this is terms so that we can be careful to reference each of these things. Okay? That starting material that drives this reaction we refer to as the substrate. Okay? Because sometimes the substrate could be massive and I don't want to draw it out. So I could just write the rate law as rate A equals K times substrate. Done. Okay? We have the nucleophile. Okay? Somebody mentioned another thing that we had floating in there. In fact, Felicia, you were the one that mentioned it.
I don't remember.
It's okay. There's a hint. It shows up right there at the end. That iodine is a leaving group. Okay? And one of the things that isn't in this list would be the snake. No. Substrate, I already said. Solvent. Okay? So when we go through and address and look at these reactions, what we're concerned about is how each of these pieces interact with this individual mechanism. Okay? So let's start to draw some connections out of this. Okay, so this is all SN1. Okay, and we will come back to these on a much prettier slide. Okay, probably multiple times. Let's start with that substrate. Okay, how important is the substrate to the reaction? Really important. It's literally what drives the reaction. You get rid of the substrate, we don't have a rate anymore. Okay, so the substrate is very, very important to this reaction. Okay? Could I change the substrate? Yes. How? Damn it, that's a harder question. How do I change the substrate? What was our substrate? Just pointing up it. What part of that structure was the substrate? So I did hear an aspect, and I heard the follow-up to it, which is even better. You said the I. The I is arguably the leaving group. So what's the substrate? The carbon. Okay? Iron carbon chain. Do I care about all these other carbons? Kind of maybe. So let's hedge the bet a little bit. Do I care about the carbon where the iodine is? Yes, absolutely. Okay? Do I care about the things connected to that carbon? Yeah, why might I care about that? Well, if the iodine leaves, what do I produce? A carbocation. And because carbocations are super stable, I don't need to worry about what's connected to it. False. Good. I do really care. Carbocations aren't stable. Okay? So for this reaction to occur, what can you tell me about that carbocation? Should it be stable? If it is unstable, can the iodine leave? Tyler, you're shaking your head. Hopefully you were shaking your head at me and not at whatever was going on in your head. That's okay. Why? Why can it not leave if this is unstable, if the carbocation is unstable? We've actually addressed this on multiple times. We addressed it through resonance. Okay? We drew an arrow, right? And if we exceeded the octet, we said we can't draw that structure, but we could use it to interpret. Right? Okay? And if our interpretation was that all we could do is go backwards, well, we don't go through that resonance. Well, the same thing's happening here. If this structure is not stable, can I continue on? If it's not stable, does it exist? Nope. Goes right backwards. That structure needs to be as stable as humanly possible, because if it's not stable, it doesn't happen. How would that affect my energy diagram if I made that intermediate more stable? That intermediate drops in energy. What happens to my activation barrier? It drops, which means the reaction goes faster. Make that carbocation stable, reaction goes faster. How do we evaluate carbocation stability? How many carbons are connected to it? A tertiary carbocation was more stable than a secondary, more stable than a primary. What kind of carbocation do I have drawn? Secondary. What if instead of that being a hydrogen, it was a carbon? What does that do to the stability of this carbocation? It increases its stability, so it drops its energy. What happens to the rate of that substitution? It accelerates. So when I look at the substrate, that starting material, what am I going to look for? I'm going to look for a carbon where the leaving group is attached, and I want that carbon to be as highly substituted as possible. Okay? I want it to be tertiary over secondary, over primary, over zeroary. How important is that difference? Okay? In stability, the primary and the zeroary are so unstable, they don't exist. So I can look at my substrate in just a simple analysis of the substrate. That is a secondary alkyl halide. SN1 will happen. I can predict if the reaction is going to happen just by looking at the substrate. That's pretty cool. Okay? Nucleophile. Because that's another piece in our reaction. The nucleophile is one of these pieces. Do I care about the nucleophile? What happens if I make the nucleophile more nucleophilic? It's going to attack faster. So if I make the nucleophile more nucleophilic, what does that change in my energy diagram? It's going to be faster. So what is it changing? That itsy bitsy tiny little arrow there? It changes that. It makes it smaller. Is that going to affect the rate of my overall reaction?
No.
No, because this giant freaking arrow in front is what's going to dictate it. Do I care to make my nucleophile stronger? No. So in fact, when I look at the SN1 mechanism, do I care at all about the nucleophile? I just care that it's there. How do I know I have a nucleophile? Not quite a charge. How do I know I have a nucleophile? I have electrons. A strong nucleophile would be negatively charged. Why would a strong nucleophile be negatively charged? Because it has a charge. Yeah, and when we go through and evaluate our rankings for stabilities, we start with, charge. There it is, right out of the gate. So a strong nucleophile will start charged. Okay? When I look at the SN1, I don't care about the strength of the nucleophile. Okay? So it's kind of irrelevant. What we will find when we go through and look at the SN2 is the SN2 requires a strong one. Which means instead of saying irrelevant for my nucleophile here, I could say weak. So if I look at my nucleophile and I'm like, that's a weak nucleophile, that's probably an SN1 reaction. Just because I pieced out the crap that we just drew on the board. Really? Yes. That's why this is cool. This is why mechanisms are so important. This is also why students tend to struggle in OChem. Everything we drew up there with that mechanism was all Unit 1. We had to apply all of that knowledge forward. Once we applied it forward, now we could go through and do all these rankings. What if you didn't make that connection? Guess what all of this is? Almost gibberish. Brand spanking new. So what do? You memorize it. Of course you freak out if there's too much memorization because you weren't properly shown the connections to the stuff that we learned already. Okay? That doesn't mean those connections are there. Okay? I'm not saying you're now geniuses. Okay? Okay? You do still need to work at those connections. But that's why we go through those connections. That's why we talk about that first, is to establish that so you can now make these parallels. Okay? Leaving group. That's important, right? The leaving group has to leave. When does the leaving group have to leave? For which mechanism? SN1 or SN2? Both. So when do I need a good leaving group? All the time. Is looking at the leaving group really that relevant? No. Okay? At least in deciding which mechanism. So I would argue the leaving group isn't a big deal. I do need to make sure that I have a good leaving group. Because if the leaving group isn't good, it doesn't leave. Okay? So I have to make sure my leaving group is as stable as possible. What would make a leaving group stable? No charge. Awesome. You jumped right at the very beginning of that. You started with charge. And you said stability means no charge. What's the next thing you would look at? Size. Is it really big? Cool. Then it's probably a good leaving group. Next thing. Electronegativity. Next thing. Resonance. Next thing. Induction. We're using the exact same rules. We're just applying them to a different definition. Okay? Last thing. This one's a giant freaking mess, by the way. What's the last one that isn't written up there yet? Snakes. No. Solvent. There we go. See? Now, whenever you see a question about solvents, you'll imagine like these snakes crawling out of the question. It'd be fantastic. Okay? Solvents. Okay? Solvents are tricky to deal with. Okay? So let's kind of slowly piece through this because we will see it come back and haunt us and we'll go through it again in more detail. So I'm not super concerned about nailing it perfectly this time. Okay? What is the role of the solvent? To dissolve the solute. And ultimately, not just the solute. How many solutes are there? 2 solutes. There's the nucleophile and the substrate. What charge is our nucleophile? Negative. What kind of solvent am I going to want? A really polar one. What charge is my substrate? No charge. Am I going to want a really polar one? Probably not, because it probably won't dissolve. So my first pass for my solvent is to make sure I pick a solvent that is a happy medium that dissolves both those pieces. So what could potentially dissolve both those pieces in this case? Probably a polar solvent. A non-polar solvent isn't going to touch the nucleophile. The nucleophile was charged. Okay? So this is where knowing those solvent classifications that we talked about is kind of important. What were those solvent classifications? Polar protic, polar aprotic, non-polar. Okay? Knowing those classifications. So in this case, I don't want non-polar because that doesn't get my nucleophile. I don't want polar protic because won't get the substrate. So my solvent is polar aprotic. Okay? That might be my first pass at this. Okay? Could the solvent affect other things? Okay, so when we said this, we just said the reactants, okay, which was the nucleophile in the substrate. And through the course of the reaction, we never made another reactant that might be called, say, an intermediate. Oh, wait, we did. What can you tell me about that intermediate? It's positively charged. And that intermediate, for my reaction to go faster, should be higher in energy or lower in energy? Should go faster. That intermediate needs to be lower in energy. So that activation barrier at the beginning is really, really small. Could my solvent potentially be used to stabilize that positive charge? Yes. What would the solvent have to supply to stabilize that positive charge? Electrons, not a proton, because a proton would be positively charged. I drop a positive charge on that, that screws it over. Okay, so I need the biggest amount of electrons possible. Where do I get the biggest amount of electrons? A protic solvent. Why? The hydrogen can be removed very quickly because I have oxygen, nitrogen, or fluorine, which are the most electronegative elements, which generates the largest partial negative. That large partial negative can be used to stabilize the intermediate. If that intermediate energy drops, that's going to cause a significant drop in the activation barrier. Because remember Hammond postulate, the transition state is closest to the one that's closest to it. Because it's an endothermic reaction, my focus is actually on that carbocation. So the solvent that I'm going to choose is not actually polar aprotic. It will actually be polar protic. I may lose a little bit of solubility of my starting substrate, but the starting substrate can very quickly leave or have the leaving group leave. I form the carbocation, smack dab, there's my reaction, running right out of the gates. The solvent can help it. Chapter 8. Da. Curtsy.
I have a question.
That is all SN1.
So if we're deciding on like a good solvent, are we always going to look at the intermediate if it's SN1?
If you're going to decide on a good solvent, are we always going to look at the intermediate? No. If it's SN1, yes. Okay? For the SN1, the most important thing is that leaving group leaving. Okay? Because that is our rate determining step, I'm concerned about that activation barrier. That activation barrier is closest to the intermediate in energy. So if I can drop the intermediate energy, my activation barrier drops. Okay? So in an SN1, yes, I'm going to be primarily concerned about the carbocation. Didn't mean to say it that way. Let's try that again. I'm going to be primarily concerned about the intermediate. The intermediate in this case happens to be a carbocation. So when I say SN1, you should immediately say carbocation. SN1, carbocation. Okay? If we go back and look at it, substrate, tertiary reacts over secondary. Why? Tertiary carbocations are more stable than secondary. Do I care about the nucleophile? Meh. Do I care about the leaving group? Meh. Solvents. I'm picking polar protic because The product stabilizes the carbocation. Okay? So if I can tie carbocation to SN1 in my brain, a lot of these memorization things start to trickle out and make more sense. Start. Just a start. Okay? You should be able to do the same thing for the SN2 reaction. Okay? Use colors. Use all those pieces. Okay? I want to break and make at the same time. Draw out what that means as a mechanism. Identify the substrate, the nucleophile, the leaving group. Okay? Look at what the solvent should be. Look at leaving groups. Look at nucleophiles. Look at substrates. Look at energy diagrams. And evaluate, if I change these angles, what happens to the overall reaction? Does it go faster? I'm going to pick that thing that makes it go faster. Okay? And what you'll find is that the conditions for substrate, nucleophile, leaving group, and solvents are different for the SN1 versus the SN2. Which means when I draw a reaction and ask you to predict the products, you can look at it and evaluate and say the substrate's tertiary. That favors SN1. The product is going to be SN1 based. Neat. Okay? So these are the big, broad pictures. Okay? So, I'm going to ask you to sort of forgive, I believe, the colloquialism. Are you ready for the kick to the nuts? Or just the sucker punch?
Yeah.
Are there other things that we have to watch out for? Potentially complications and or benefits of these reactions? Yes. Okay. Back in chapter 7, when you saw a carbocation, what did you potentially do? You did a rearrangement. Do we form a carbocation? Could this, instead of doing just a nice, sweet, simple substitution at one position, could it possibly rearrange? Yes. For an SN1, you have to watch out for rearrangements. You have to watch out for the rearrangements because carbocation. But what did I tell you to memorize with SN1? Carbocation. Oh, yeah, look, there it all matches up. Okay? So if you remember SN1 is carbocation, when you do an SN1, you're like, stupid rearrangements. Okay? Everybody's favorite chapter is now about to hit you. Chapter 5. Okay? And so with that, I kind of want to delete most of the stuff up here to clean it up a little bit. We okay with that? Chapter 5. And you're thinking, what was chapter 5? I'll remind you. So let's clean this all up a little bit. I don't care that that's heterolysis anymore. I don't really need that big reaction thing there. Can delete all that. For that matter, I don't even really care about the nucleophile. I don't care, that's coordination. So someone heard chapter 5, someone heard stereochemistry, and then someone went, Is our starting molecule chiral?
Yes.
Yes. Is our final product chiral?
Yes.
Then what's the big deal?
Is it S or R?
Is our intermediate chiral?
No.
No.
Okay. I could start with a starting material that is chiral, and in the SN1, I end up with achiral products. There's only one structure. Okay, well, let's walk through it.
Can a molecule go from like R configuration to S or R to R depending on
Okay.
like how it connects?
And actually, let's redraw that. Whoops, not that eraser. Okay. Let's make the hydrogen dashed. Make that wedged. Let's make this R a CH3. Everybody okay with that? I want you to tell me stereochemistry of the product. So I'll walk through the first one, okay, the reactant. Okay, we go through and assign priority. for our chiral atom, that carbon. 1, 2, 3, 4. The hydrogen's aimed away from us, so we go 1 to 2, 2 to 3. I am going clockwise, so that is R. Right? So now what I would like you to do is take a little bit, look at the mechanism as we've got drawn out, and predict, should your product be R or S? To drawing the meme. Sorry. Why not? For those of you who are like, oh my God, that's awful, you freaking draw it and then come back and talk to me about it. Why not both? What happens in the very first step? I break a bond. The iodine leaves. And I form a carbocation. Where's the carbocation? What is a carbocation? I'll accept a positive carbon. Keep going. Sort of. So I got a reference here that this is an sp2 carbon. I do accept that, but that's not a carbocation. What is the carbocation? It's not sp2, it's the remaining piece. What's the remaining piece of an sp2 hybrid? No. So let's pause and go back to this remaining piece. sp2, we're talking about the atomic orbitals. So if I look at the atomic orbitals for an atom, I have S and then I have 3 P's. If I have an sp2 hybrid, what's left over? A p orbital. Where does the p orbital exist? If this is my drawing, where is that p orbital? It is perpendicular to the plane of the paper. It's coming out of the plane of the paper and behind the plane of the paper. So if we take this molecule and I just kind of rotate it a little bit, I don't remember how many carbons there were. There's our magic p orbital. Where can I place electrons into that p orbital? On either side of it, because there's a lobe there. There's a place to put the electrons, which means the chlorine can come in from the bottom or from the top, which means when I get the result, I could go through and show that the chlorine came from the bottom and it would be dashed. Or the chlorine could have come from the top and it would be wedged. When I go through and assign chirality, the R and the S, guess what I find? I get both. Both of these come out. This is a massive complication of the SN1 reaction. This is one of the reasons why chemists don't use the SN1 reactions. Right? We tend to minimize our access to them because the end result of virtually every SN1 reaction is 2 products. That's a bit of a problem. Okay? If we only want one, we've now created a bunch of trash that I'm not going to use. The best yield I could get is 50%. Okay? That's not a stellar yield. Okay? So the big complication for our SN1s is that we have that carbocation, we get both attacks on the carbocation, on that p orbital. Okay? Which means I get 2 products. Okay? There are ways to limit that, manipulate that. Ultimately, the best way to manipulate it is don't run a type of reaction that involves the SN1 mechanism. Okay? So now we've covered all of SN1, even like the benefits. You really want to call those benefits. Okay? Rearrangements, more chemistry that you have to worry about, or chirality that you have to worry about. Okay? So we've now addressed all the aspects that you need to do with SN1. What I do want you to go through and do is try to do that for the SN2. Okay? And I want you to do that on your own time. We will go through and talk about it. Okay? But we aren't going to talk about it at this speed. And for those of you going, well, this was really fast, it's only getting faster. Okay? So you need to take that time to go through and look at the SN2 just like we did here. Does that make sense? Okay. So with that, we'll go ahead and continue and talk more in depth about each of the substitute. Oh, no, we got to do the elimination. That's right. I forgot about that. I didn't, actually. I was just kind of being sarcastic. We want to use the exact same logic that we just used with the substitution. What changed? Okay. We formed a pi bond. So there's the formation of a pi bond. Is that it? Nothing else changed?
You also got rid of a hydrogen.
I lost a hydrogen, so I broke a sigma to a hydrogen.
There's also a leaving group that left.
Okay. And I broke a sigma to a leaving group, or in this case, what we called is X. Okay. The hydrogen is not a leaving group. We'll address that also when we get through it. So what immediately jumps out at you of like, oh man, really? Is this harder or easier than the substitution? Why is it harder?
Because you don't know which one is first.
Okay. In the substitution, how many things happened? 2 things. Broke, moke. Made. Made and broke. Okay. Broke, moke worked better. Okay. In this case, I've got 3 things going on, which means if we go through and attempt that same arrangement of looking at all the possible ways that this could happen, we're going to get a lot more options that we have to evaluate. And Raph is already like, this is stupid. I don't want to have to go through and do that. I agree with you. I don't think you formed a pi bond. What did I just draw?
The first best or the first? Hell. First worst?
First worst resonance structure. The formation of the pi bond is really just the negative and the positive, just aligned in this fashion. Okay? So I didn't really form a pi bond. I can eliminate that from my answers. Okay? I'm just going to form the Zwitterion. The Zwitterion resonates to show the pi bond formation. That's an easy step. So really all that's happening is that I break a sigma to a hydrogen bond and I break a sigma to a leaving group. The end result is that when I break the leaving group bond, because it's a leaving group, what is it doing with the electrons? It's stealing them, which means the carbon comes in positive. What happens when I break the carbon-hydrogen bond? Why would the carbon take the electrons from the hydrogen? Yes. Carbon is more electronegative than the hydrogen. It's not by a lot, but it is there. Okay? Is that an easy bond to go through and break? No, why not?
Because the difference is so small.
That difference is so small. Okay? So it would be really helpful if I say added something that could potentially rip the hydrogen from the structure, leaving the electrons behind. So the hydrogen would get ripped off as a what charge? As a positive. And those of you starting to mumble in the other word that you thought I was leading towards, which was the next goal,
Acid base.
it is an acid. I'm trying to make that starting material act as an acid. So what could I add to help it act as an acid? I could add a base. So instead of adding a nucleophile, I could add a base. That base is going to help to remove that bond, allowing the formation of the pi bond. So cool, it's really only 2 things. Okay? I break the sigma to the hydrogen. I break the sigma to the leaving group. Okay? So 2 things means 3 possible ways to do it. Guess what? 2 are valid. And those 2 being valid, guess what they also do? They perfectly mirror the substitution pathways. Okay? So because we did SN1, let's go through and do this one as E2, which means I need to break that X sigma and make that carbon hydrogen, since I've been doing it this way, that hydrogen sigma simultaneously. Okay? So what would that mean as a, oh man, it's totally in the way. Okay, so you're just going to remember that that was there. Is that okay? That's what we're doing? Yeah? Okay. How do I show arrows for this to happen?
So for the carbon hydrogen, you draw the arrows coming from the bond.
So, okay, so let's add a little bit of clarity here. We've got our carbon hydrogen and our carbon leaving group, so we'll call them red and blue. Okay, so you're telling me I should deal with
The
red. Where does the red?
the carbon takes the electrons, so is it the red wants the nitrogen.
Okay. What does the arrow show the motion of? The movement of electrons. I'm glad that you thought through that on your own. I'm still going to draw it. Okay. What happened to the bond? It's no longer there, right? Where did the electrons in that bond go? According to our arrow. To the hydrogen. Okay? And I'm still glad that you're doing that. Now let's add our charges. Positive carbon, negative hydrogen. What is our leaving group going to do? Do the exact same thing, which would put a positive next to positive. So that's kind of questionable. The other part, would I expect hydrogen to come off stealing the electrons from carbon? No. Now we get a myriad of reasons. So let's start lining them up. Why does the hydrogen not take the electrons from the carbon? Okay. It is less electronegative. The hydrogen is less electronegative than the carbon, then it's not going to steal it. That's fine. Now our next sequence. Charge. It's charged as a leaving group. That's not a good thing. Next thing, size. Hydrogen is literally the smallest atom that we could possibly put charge on. Not a good option. Next, electronegativity. As far as our nonmetals go, it's pretty much the least electronegative. Okay? That's not 100% true, but it's pretty much as low as we can go as a nonmetal. That's not a good option. Okay? Next. Resonance. Is there any resonance to stabilize that negative hydrogen? No. Induction. Are there any other atoms that the hydrogen could displace that electron to in that molecule? No. Nothing about H- says stable. Okay? So I'm perfectly all right with that. I want you to go through and do that. I want you to draw that arrow and be like, God, that sucked. Don't tell me, God, that sucks. Draw the result and be like, yeah. There's the evidence that, yes, what I did was horrible and awful, and I should be forever in misery because of it. Okay? So now that I know I drew the arrow the wrong direction, what can I do? Now we can change it. And where do I want to change that arrow to go? Towards the carbon. Okay? That would be all fine and dandy. So we could draw that result out. What happened to the bond? It's gone. So there's my hydrogen. Where's the electrons? On the carbon. What charge would that carbon be? Negative. What charge would that hydrogen be? Positive. I love the arrow, but I don't love that you stopped. Admittedly, I interrupted you. So why? What did we say was going to happen for this particular drawing? I needed to do it simultaneously. What have you done so far? I just broke. Okay? And I just broke the carbon to hydrogen bond. I have done nothing about breaking the leaving group bond. Okay? So if this is going to be more appropriate, I need to show that happening at the exact same time. Okay? So, how do I fix it? Draw another arrow. See? Whenever something's wrong, just draw more. Okay? Where's that other arrow?
The CX bond to the X.
The CX bond to the X. Why should it go towards the X? That atom we're just assuming is our leaving group. It's the more electronegative one. It's probably larger. All of these things are going to contribute to it withdrawing those electrons. Which would mean, at the end of that, what would I draw? A positive carbon and a negative carbon. This would be the Zwitter ion that we said was right there, so we could thereby go through and show the resonance to get us to the final answer, which I need to fix that. We would need to show in this fashion. Why do we show it in that fashion? It's more realistic to the three-dimensional structure because those are sp2 carbons. Okay? If we wanted to add the curved arrow, we could go through and do that. Okay? There's a couple big things that are going to be questionable within this work. Number one, our arrows are showing us go to the formation of the Zwitter ion. Is the Zwitter ion the most stable Lewis structure? No. So the instructions we're providing are providing them to do something not good. It's not horrible, but it ain't good. Which means our instructions could be better. Okay? Where do we want our instructions to end at? The product, which is with the final pi bond. Okay? Well, I know I have to add that extra arrow. I'm taking the electrons from the carbon and going to the bond in between to make the pi bond. Does that carbon have electrons in our starting material? Does it have that lone pair yet? No. So if it doesn't have them yet, how can I show an arrow that would allow me to do that? Well, this means we have to go back and think about the arrows that we're allowed to show. We can go from a bond to an atom. We can go from an atom to a bond. We can also do bond to bond. I'll take the electrons from that carbon-hydrogen and I will immediately dump them into that proximal bond. The end result is I immediately jump straight to the formation of that pi bond. Okay? So that is the first aspect behind this. The next part, you are showing carbon taking electrons from hydrogen. Is that bond an easy bond to break? No, that's a nonpolar bond. I want to help that bond break. How do I help that bond break? I add a base. Okay? Describe to me that base. It would need to accept a hydrogen by doing what? Donating electrons. So it might be useful to show a pair of electrons. Let's think about the characteristics of said base. Does all it need to do is have a pair of electrons? Is that an easy bond to break? No. If it's not easy to break, what are you going to need?
Strong base.
Something really strong. Let's make that a strong base. How do I make sure that that stands out now as a strong base? No. Hydroxide is a specific strong base. I didn't ask for a specific one. What makes it a strong base? There it is. We now have a strong base attacking the hydrogen, which removes the hydrogen from the structure. The electrons go to form the pi bond. At the same time we form the pi bond, we kick out the leaving group. We end with our elimination product. How many steps did this take? 1. Why is it E2? That's a good question for Monday.